Hi, and welcome to part 5 of our Flow360 training. Looking at our expanded visualization of the training structure, you can see we are in the advanced topics, and this session will provide an overview of rotor modeling. First, I will give a high-level introduction to each of the 5 rotor models we support. Then I will explain the theory behind how each model works and how it is implemented. Next, we will compare the models in terms of fidelity, accuracy, speed, and computational cost, so you can choose the right approach based on your application and budget. Finally, I will walk through example setups for each model and show how the results typically look. Now let's jump in. Flow360 supports 5 rotor model options, spanning a wide range of fidelity. The lowest fidelity option is the actuator disk model. Next are blade element theory disk and blade element theory line. The BET disk formulation is steady, while the BET line formulation is unsteady. After that comes the multiple reference frame model, also known as MRF. The highest fidelity option is fully resolved, unsteady blade simulation using sliding interfaces. Each model represents a different balance of accuracy, cost, and runtime. Higher fidelity models capture more physics but require finer meshes and more compute. We will start with introducing more on the virtual blade, or disk-based models, which include the actuator disk, BET disk, and BET line approaches. In these models, the rotor blades are not explicitly resolved. Instead, the aerodynamic effect of the rotor is modeled by adding momentum source terms to the governing equations within a defined volumetric region. This approach avoids resolving blade geometry and boundary layers, which significantly reduces mesh size and computational cost. Because the smallest mesh cells are larger than in resolved blade simulations, convergence is typically faster and more robust. The simplest model is the actuator disk, which is often used in conceptual design when limited rotor information is available. You typically provide thrust and torque, or thrust per unit area, and the solver applies an equivalent pressure jump across the disk. There is no feedback between the local velocity field and the applied forces. As a result, actuator disks do not capture interaction effects or inflow variations. They are best suited for early-stage design or for studying gross downstream effects of a rotor. Next is BET disk. This model includes feedback from the local velocity field. It uses airfoil tables and rotor geometry, combined with the local flow velocity, to compute forces. From the local relative velocity and blade orientation, the effective angle of attack is calculated. Lift and drag coefficients are then used to compute axial and circumferential forces, which are applied as momentum sources. This model is steady in time and relatively fast to run. BET line is similar to the disk formulation but includes azimuthal variation. The blade position changes with azimuth, allowing the model to capture unsteady effects. This provides time-accurate rotor behavior without fully resolving blade geometry. Because it is unsteady, it is more expensive than the disk formulation, but captures additional physics. The next model is the multiple reference frame, or MRF. In this approach, the rotor blades are explicitly meshed, but not physically rotated. Instead, a rotating reference frame is applied to a cylindrical region containing the blades. This creates the effect of rotation while keeping the simulation steady. MRF assumes axisymmetric flow at the interface between rotating and stationary regions. As a result, it works well for axial flow, but is not suitable when strong non-axial or side-slip effects are present. MRF can be run in either steady or unsteady mode. The highest fidelity option is fully resolved, unsteady blade simulation using sliding interfaces. This setup is similar to MRF, but the rotating region physically rotates during the simulation. This captures blade motion, wake development, and interaction effects more accurately. It is the most computationally expensive option, but provides the highest level of fidelity. Now we can briefly compare these models. This slide shows the results for the XV15 model. As you will see from this slide, BET and MRF do well in axial flight. The bottom left graph highlights this, showing results within 10% of each other. If that level of accuracy is sufficient, lower fidelity models can be used to save significant computational cost. The graph on the right shows experimental data compared to 3 different Flow360 results. BT disk has some over-prediction in figure or merit, but BET line and fully resolved unsteady simulations are very accurate compared to the experimental results. There are limitations of the BET methods at high angles of attack or in highly separated or transonic flows. Because it relies on two-dimensional airfoil tables, it cannot fully capture strong three-dimensional effects, shocks, or complex separation. In these regimes, MRF or resolved blade simulations perform better because the blade geometry is explicitly resolved. MRF also has its limitations. It assumes azimuthal symmetry, so it does not handle non-axial inflow or strong asymmetries well. Blade element models can handle some non-axial effects, but only up to a point. From a cost perspective, blade element models are significantly cheaper than resolved blade simulations. Because the blades are not meshed, node counts can be reduced by roughly a factor of 2 or more, depending on the configuration. Blade element disk models are even cheaper because they are steady. Many of our existing users generate aerodynamic databases using steady blade element simulations, then validate a small number of cases with resolved blade simulations. Now, we will discuss meshing recommendations for these models. For actuator disk and BET models, local volumetric refinement is required where the momentum sources are applied. This region must be refined enough to accurately resolve the imposed pressure jump. A general recommendation is to use a disk thickness around 10 to 15% of the radius. Adequate axial resolution across the disk is important with at least 15 nodes in the axial direction. Radial and circumferential resolution requirements are less strict, but should still be sufficient to avoid large gradients. For MRF and resolved blade simulations, the rotating zone must be a body of revolution with a clearly defined rotation axis. When using Flow360's automated meshing, the sliding interface must be cylindrical. If you are meshing using third-party software, non-cylindrical rotating regions are supported as long as they are axisymmetric. The sliding interface must not intersect solid walls. The rotating region must fully enclose the blades without cutting through solid geometry. Both conformal and non-conformal meshes are supported. Correct rotation direction is important for blade element models. Flow360 supports both left-hand and right-hand rotation conventions. The rotation axis and direction must be consistent with blade orientation. If results appear incorrect, visualizing slices through the blade element region can quickly confirm whether forces are applied in the correct direction. Now we will briefly walk through the setup for each model. For actuator disks, you specify thrust and circumferential force per unit area as a function of radius. This can be done in the web UI or via Python. Inputs can be provided through CSV or JSON files, which are plotted in the UI for validation. Blade element disk setup requires a bit more detailed inputs, including chord distribution, twist distribution, airfoil tables, Reynolds number and Mach dependencies, and rotational speed. Because of the complexity, the Python API is recommended. Converters are available to translate data from common rotor analysis tools into Flow360 compatible JSON formats. For airfoil sectional polars, we have a few guidelines. When setting up the Python object, make a nested list in the order of Mach number, Reynolds number, and alpha. Continuity across the full angle of attack range is important for numerical stability. Sudden discontinuities in lift or drag curves can cause convergence issues. For chord settings, distribution should not be non-zero at the root radius, as this would lead to infinite solidity. Either start the blade away from the root or ramp the chord smoothly from 0 to represent a hub. Some additional BET disc setup tips are that sectional radiuses for airfoil tables can be different from the distribution radius for chord and twist, meaning you will provide 3 different distributions for chord, twist, and airfoil tables and specify at different radial locations, and it will assume a linear distribution. The inputs of N loading nodes and chord ref are only used for the sectional loading, output scaling, and distribution, and do not affect the simulation result itself. The last thing is how you can graphically examine BET polars, chord, and twist distributions using the web UI using the Visualization tab. For blade element line simulations, there are just a few differences from the blade element disk setup. This includes activating the unsteady solver in time stepping and setting inputs for relative tolerances in the Navier-Stokes and turbulence model solvers. In the BET disk input, a blade line chord should be set to approximately 1.5 times the reference blade chord, along with specifying the initial blade direction, which specifies the position of the blades at the start of the simulation. MRF setups require defining the rotating volume and mesh at the boundary between the stationary and rotating volumes. You then apply a rotation to the rotating volume. MRF is activated automatically when time stepping is set to steady and the rotation is applied. Unsteady resolved blade simulations follow the same setup as MRF, but you will switch to unsteady time stepping. So the rotating region physically rotates and switch from absolute to relative tolerances. Finally, Flow360 provides tutorials and example scripts for blade element and time-accurate rotor simulations. These include setup, meshing, post-processing, and visualization examples. If any part of the workflow feels unintuitive or time-consuming, feedback is encouraged so the tools and documentation can be improved. With that, we have now concluded the 5th training session on rotor modeling. As you continue your onboarding, we recommend that you continue to use and reference our online documentation. We would also appreciate to hear your thoughts and feedback, so we can continue to make improvements and shape the development of Flow360.